Look, here is a beehive. The worker bees are busy cleaning the hive. Take a look at these numbers. Do you observe any pattern in these groups of numbers? Yes. These numbers can be grouped into prime and composite numbers. Here are the numbers 2, 3, 5 and 101 are grouped as primes. These numbers divisible by 1 and itself are called prime numbers. So, a prime number is a whole number greater than 1 that can be divided only by 1 or itself. Similarly, the numbers 6, 10, 12 and 102 are grouped as composite numbers. These are numbers that have at least one other factor besides the number 1 and itself and are called composite numbers. Thus, a composite number is a number that has at least one other factor besides the number 1 and itself, like 4, 6, 8, 9 and so on. Now, let us have a recap on some important key terms. Take a composite number 10. The number 10 can be expressed as a product of two prime numbers 2 and 5. So, numbers 2 and 5 are the factors of 10 as they both can evenly divide 10. Thus, factors of a composite numbers are those numbers that can evenly divide it. Consider the composite numbers 6, 35 and 27. 6 has the factors 1, 2, 3 and 6. 27 has factors 1, 3, 9 and 27. 35 has factors 1, 5, 7 and 35. What do you conclude from this? The numbers 6 and 35 have no common positive factor other than 1. So, they are called coprimes. The numbers 6 and 27 have the factor 3 in common. They are not coprimes because they are both divisible by 3. Two integers are said to be coprime or relatively prime if they have no common positive factor other than 1. What are the factors of 60? Let us go step by step and get the factors of 60 using a factor tree. Start dividing from the smallest prime number, which is 2. So, 60 divided by 2 is equal to 30. The number 30 is not a prime, so we need to factorize it further. Here, 30 divided by 2 is equal to 15. The number 15 is not a prime number. So, dividing by the next largest prime number, which divides it evenly, we get 15 divided by 3, which is equal to 5. Here, the number 5 is a prime number. We stop dividing it further. The method is called prime factorization. Thus, the prime factorization of 60 is a product of the circled factors, which are prime numbers. Thus, 60 is equal to 2 into 2 into 3 into 5, that is equal to 2 square into 3 into 5. Thus, prime factorization is a method of finding which prime numbers you need to multiply together to get the original number. In the above example, we saw that the prime factors of 60 is equal to 2 square into 3 into 5. There is no other possible set of prime numbers that can be multiplied to make the number 60. What do you conclude from this? This leads us to a conjecture that every composite number can be written as a product of power of primes. There is only one unique set of prime factors for any number. In fact, this statement is true and is called the fundamental theorem of arithmetic. The fundamental theorem of arithmetic states that every composite number can be expressed as a product of prime numbers, and this factorization is unique, apart from the order in which the prime factors occur. The fundamental theorem of arithmetic has many applications both within mathematics and in other fields. YB's friend is trying to recall where he had used the fundamental theorem of arithmetic earlier. To find this out, let us solve a problem of finding the LCM and HCF of two numbers 12 and 32 using prime factorization. The prime factors of 12 are 2 into 2 into 3, that is equal to 2 square into 3. Similarly, the prime factors of 32 are 2 into 2 into 2 into 2 into 2, that is equal to 2 to the power of 5. Recall, HCF is the product of the smallest power of each common prime factor in the numbers. So, the HCF of 12 and 32 is 2 square, that is equal to 4. Recall, LCM is the product of the greatest power of each prime factor involved in the numbers. So, the LCM of 12 and 32 is 2 to the power of 5 into 3, that is equal to 96. What do you observe? Here, we see that the prime factorization of natural numbers is unique except in the order of its factors. Is it not the fundamental theorem of arithmetic that we have studied earlier? Yes, we have been using prime factorization to find the LCM and HCF of two numbers, which is nothing but the fundamental theorem of arithmetic, even without realizing it. Solving problems using HCF and LCM. HCF and LCM can be used to solve many problems in real life. How do you decide which one to use where? HCF should be found when you have to split things into smaller sections. You are trying to figure out how many, for example, the number of people you can invite for a party. You are trying to arrange something in rows or groups. LCM should be used when you have an event that is or will be repeating over and over. You have to purchase or get multiple items in order to have enough. You are trying to figure out when something will happen again at the same time. YB has been going around inviting lots of friends to his birthday party, but we have only 120 chocolates and 36 books as return gifts. What is the largest number of friends YB can invite so that each of them has equal number of chocolates and books in the return gift pack? To solve this, do we need to use LCM or HCF? We need to use HCF as we are trying to find the largest possible number to invite. We know that YB has 120 chocolates and 36 books. Using prime factorization, we get the prime factors of 120, that is equal to 2 cube into 3 into 5. The prime factors of 36 is equal to 2 square into 3 square. Recall, HCF is the product of the smallest power of each common prime factor in the numbers. So, the HCF of 120 and 36 is 2 square into 3, that is equal to 12. Thus, YB can invite maximum 12 friends to his birthday party so that each has equal number of chocolates and books in the return gift pack. Now, let us solve another real-life problem. YB is organizing a car race game for his friends and he is putting 2 tracks for this. He has 2 boxes of track pieces. The first box has 8-inch pieces and the second box has 18-inch pieces of car track. How many of each piece would YB need to build tracks that are equal in length? To solve this problem, do we need to use HCF or LCM? We need to use LCM as we are trying to find out maximum number of track pieces to build 2 equal length tracks. Here, it is given that the 2 numbers are 8 and 18. Let us find the LCM using prime factorization to solve the problem. The prime factor of 8 is 2 cube and the prime factor of 18 is 3 square into 2. The LCM of 8 and 18 is 72. YB needs to build 2 72-inch tracks. Now, to determine how many pieces from each box YB will need, we have to divide 72 by 8, that is equal to 9, and 72 by 18, that is equal to 4. Thus, YB needs 9 8-inch pieces of track and 4 18-inch pieces of track. Where else do you find the use of fundamental theorem of arithmetic in real life? Fundamental theorem of arithmetic plays a key role in cryptography and is widely used algorithm to calculate the secret codes. Cryptography is a set of techniques used for hiding information. It is widely used in ATM cards, computer passwords, and buying and selling goods over the internet. In the earlier example, we determined the LCM and HCF of two numbers 12 and 32. What relationship do you observe between LCM and HCF? We notice that HCF 12, 32 into LCM 12, 32 is equal to 12 into 32. So, an interesting relation exists between the HCF and LCM of two positive integers a and b. HCF a, b into LCM a, b is equal to a into b. Now, let us solve an example to verify this. The HCF of two numbers is 119 and their LCM is 11,781. If one of the numbers is 1071, find the other number. Let the first number be x and the second number be y. Recall x into y is equal to HCF into LCM. So y is equal to HCF into LCM divided by x. Substituting the known values and simplifying, we get y is equal to 1309. So we can conclude that the second number is 1309.